Okay, so welcome back today. So this I think is section 3, which is still part of the hard-time problem. So part of this. So what does it mean? Today we are trying to use the formula that we derived 2 weeks ago and get as much qualitative information out of it as possible. So, and also we will see a method that we will not go into the details, but how to use the formula that we derived last 2 weeks ago to implement it manually if you are interested in that. Because what we did last week, it's not necessarily clear why that is too many the formula that we got. And so let's this function USD be given by that. And please remind me, we will not erase this formula for today. We will always need it. Okay. So this is the formula that we got last week. 2 weeks ago, sorry. I will just keep saying last week. I have just confusing. And okay, this formula holds for positive imaginary part of P. So this is kappa. So this was, remember, this was the first description that we had to impose when we derived this. And for incident angle, like this. So these were the two descriptions that we imposed. So we are interested in the Harvard asymptotics, but before we can meaningfully talk about Harvard asymptotics, we need to make sense of this formula in the limit for vanishing imaginary part. And we would also like to extend the following incident angles. Why this is very important, because right now everything behaves exponentially. This was one of the reasons also why we imposed this condition. But if we are interested in obtaining like meaningful Harvard asymptotics, we want to find Harvard asymptotics that don't decay exponentially, because otherwise we will find pretty much nothing in the pathway. But we will see when we take this limit, it will not decay exponentially everywhere, so we will be able to find something interesting. Good. So and again, as a reminder, we have this spectral function. And for now, I will write down the kappa dependence explicitly. Which is this. Well, this is all reminder of what we did the last time. Yes. So this is just rewriting this using our notation. And in some sense, the problem is that as soon as kappa is positive, this function will not have any singularities on the real line, which you can pretty straightforwardly check by just looking what all of these functions do. It's not necessarily so straightforward for the square root, but it's a consequence of how we define our square root and how the branch cuts go. So I think this picture for how this function looks is also in the Sommerfeld section of my thesis. So this function looks something like this, right? These are the branch points, and then it has branch points like this. So nothing of it lies on the real axis. And well, for this, it was the normal square root. So and because this is a positive imaginary part of branch point and cut of this also never lies on the real axis. So, well, and this pole also never lies on the real axis because K has positive imaginary part, and the incident angle is chosen such that this right here is negative. So it will lie somewhere over here. But the problem is, as we now take the limit of kappa to 0, all of these singularities will move towards the real axis. So that expression doesn't make sense anymore. And in fact, it wouldn't be like this expression wouldn't necessarily convert, right? Because we lose exponential decay, which, yeah, right now we have, because this thing has positive imaginary part, so that's all perfectly well defined. So that is just to say, we cannot just take the limit of this expression. It wouldn't make sense. So further. And I will also write, yes, I probably should have done that here as well. So let's write the kappa independence explicitly. So this is our kappa vector. And surprisingly, this is reasonably straightforward. Do you have any ideas of how we may be able to do that, defining this limit? By straightforward, I mean, if you've seen it once, it seems straightforward, but do you have any ideas of what we could do? Okay, this is probably really subjective, but there are a few very, very important theorems in classical complex analysis. Do you know what they are? What would you classify as probably some of the theorems in classical complex analysis? Residue. Yes, and before you get to residue, what do you need? Exactly, and what does Cauchy allow us? Yes, but specifically, it allows us to change our integration contour. So it's like the complex analysis version of Stokes' theorem, essentially. Because what Cauchy's theorem tells you, if this is your integration contour, and if you look at an integral that goes like this, right? You can take the difference of the two integrals, and Cauchy's theorem tells you that all of these circles vanish. Meaning that the two integrals are indeed the same, because, well, whatever is not a circle also vanishes, because it just cancels each other out when you take the difference. So that is to say, let us, and it really does not matter what exactly gamma is, so I will not write down a specific formula, because you can choose whatever you feel like choosing. It only depends on the homotopy class if you want to phrase it in terms of topology. So let us choose gamma like this. Are you happy with me just drawing the picture and calling this our new contour gamma? Right, you could cut out some epsilon interval around this singularity, attach a semicircle to it, and repeat that for all singularities if you want to write down a formula. But really, you could also just use something like this that would work just as fine. So you have a lot of freedom as to how you would choose gamma. So what Cauchy's theorem tells us is, so by we find that the scatter field is equal to the, well, it's not really a Fourier integral, but let's call it modified Fourier integral maybe, over our new convergent phi alpha x2 kappa e alpha x1 b no, sorry, the other. Okay, did I forget anything? Yes, so I should write down probably. So the singularities of phi are 1 plus minus k equals a, which is a branch. Sorry, alpha. So this would be a branch. And I have, if this, can you distinguish this from alpha? So this is supposed to be an A. No? Okay. Well, let's call it A hat then. So this is so and now what I want to do is that gamma be such that for all delta that lie between 0, but they could be equal to 0, and kappa could also be equal to kappa. Gamma does not intersect any singularities. So a moment. Yeah.
So gamma is repeating this way all the way to infinity.
Yes. Yeah.
So I thought that the theorem was like about the control enclosing a singularity.
Yes. So this is why this integral, why these two are similar. Not similar, are exactly the same. Because if you look at this control, and you look at this control. Maybe a bit too many errors, but you get the idea. You look at the difference of the two integrals. So you look at the difference of these contours. Everything here will cancel out because it's just the same integral. Then goes for here, then goes for here, and then goes for here. So to show that the two are actually equal, you need to show that the integral around here is 0. Well, if you take the difference, sort of one orientation, it looks right. So then you are just left with a circle, but homotopically a circle, but you have no singularities inside. That's this assumption over here. So by Cauchy's theorem, all of these shaded regions integrate to 0 when you take the difference. So the idea is, and this idea is really important, and probably one of the most important takeaways of today's lesson. The idea is that if you have some contour, you can change it to any other contour as long as you don't have any singularities of your integral. So if you like topology, you could say that the integral only depends on the homotopy class. Well, you need to be a bit careful that you match them together infinitely, right? So that everything remains well defined. But essentially, that's the idea. As long as no singularities are hit, you can change it around. So as long as you remain in the same homotopy class, maybe let's say subject to fixed endpoints, this will work fine. Are you happy with that? Okay. This is really, really important. We will also use that all the time today. So that's why I say by Cauchy's theorem, because you can look at the difference like here. And the same works also in higher dimensions if you would look at surfaces, but then you would have to use Stokes' theorem. But the idea is the same, that you look at the difference and then look at some closed, like some integral over some closed integral over a closed form, essentially. That's what it is. Okay. Yes. So And now, why did we do all of that? Because now we can take the limit, right? This integral will formally remain well defined, so we can write down, we can plug in 0 here, like we can take the limit. All of the limit will work fine because of this condition over here. Like no matter how our singularities move, it will never intersect it. And this is also really important because if I would, well, I will first write down the result and then we will discuss why it's important, why this condition is so important. Because essentially this uniquely defines our field, right? Cauchy's theorem tells us that for every contour that we choose like this equality holds. But if I would change my contour down, like in the wrong way, then I would get an additional contribution from our singularities. We will discuss that later on, but this condition is super important. Okay, maybe let's continue over here. Okay. So right. As well. So now we define, and now we will not write the part anymore, because we will only be looking at this from now on. So define this and this interval. This is the recording this. Okay. Okay. So that's our definition. And again, what's super duper important that I have one singularity here, another here, and another here, and that in some sense I know how my contour moves around these singularities. Because we could also think maybe of writing something like this down, where gamma looks like this, right? You could think of, let's call this gamma twiddle. You could write down this integral, right? The integration contour still moves around all of the singularities. But this will not define the correct physical field. Because, well, essentially that's why you need this, right? We would not get equality of this to this for positive imaginary part of K. So it's really important to keep track of how the contour moves around the singularities. It's not enough to say that it just moves around the singularities, and again, I emphasize this because in one dimension it's maybe clear, like visually, why this would not be allowed. But in higher dimensions, where you have a lot more room to move around singularities, it's maybe not necessarily clear what the right direction is, and this will be important probably next year. Does it make sense to you? So the direction in which our contour bypasses our singularities is super important, and it's related to the physics, because this is related to us wanting this to decay exponentially, subject to some other conditions, which is related to choosing the right physical field. Because remember, in the first lecture, we had this cylinder, right? And we had two possible Bessel functions that we could have chosen. So we needed to eliminate one. So we needed one condition that selected the physical solution. Essentially, if we choose this contour, we get the antiphysical solution. We get the wrong part that does not satisfy the radiation. Anyway, long story short, this is super important. Well, and that takes the purpose. We have now defined this field for dimension increment part of our and as an exercise, if you want to, you can look at the field defined by this contour, just replace gamma with gamma triggered over here, and look where does it fail to solve our half problem, if you want. Okay, so now how do we define our solution for all possible independent angles? Okay, it's going to be a bit of a hand-wavy explanation, but again, it's Hooke's theorem. So what we do is we move gamma with A as a moves from minus A. Okay, so what do I mean by this? What will happen if I change my incident angle? This will start at minus K, but it could move all the way over to plus K, right? Because cosine just goes from -1 to 1. As theta goes from 0 to 2 pi. So what we now need to ensure is that this singularity over here, which could go all the way over here, just never intersects this, but we can just carry the circle along. So we can choose a circle with center A and move it along. And this will always be possible if we choose our circle sufficiently small, because 0 and 2 pi are not included in the interval. So A can never actually hit minus K or plus K. If it would hit, we would have a problem, but we don't do that. And physically, that does mean that our incident wave does not come from along the half K, which you can still consider like that. Okay, I have with this. So again, we use Hooke's theorem is this border moves along, we just carry this all the way along. For that value. Good. So if you're happy with that, we can now get to point 3. What we actually want to do. How many of you know the method of steepest descent? Method of steepest descent. Have you all seen that before? Roughly? Okay. Well, essentially, the rest of this lecture will all be about method of steepest descent. More so about how we can get to a point where we can apply the method of steepest descent. But okay. So what's the idea? The idea is that in some domains, and by the integral, I always mean the integral, the thing inside of the Fourier integral. Not only the spectral function, but like the spectral function, like all of this. This is always what I mean by the integral. So in some domains, the integral phi alpha x2 e minus I alpha x1 decays exponentially. So what does it mean? That means if we can change paths. So this is all not like the mathematical rigorous, it's just to give you an idea of why we are doing what we want to do. So if we can change paths, let's call them gamma gain of gamma to lie within you gain the integral over gamma gain. The alpha Okay. Exponentially. Yes. Okay, it goes to infinity. So if this integrand decays exponentially over this quadrant, by exponentially I mean as x1 and x2 go to infinity, then we can ignore it, as in this integral will decay exponentially in this limit. But we are only interested in non-exponentially decaying parts of the scattered field. So the idea is that if this decays exponentially, we just ignore our symptotic expansion. So what is our objective? Our objective is find f of x such that we scatter is equal to f of x plus terms that decay. That's what we mean by we want to find perfect escalars. We want to find this f of x. Okay. And here let's change this. Yeah. Okay. So what we need to find is regions where this thing over here decays exponentially. Because the remainder will never decay exponentially. Right. But this we have control of getting exponentially decay. So that's our first objective. So we want to find regions where phi alpha x2 decays. So look at v of alpha x witness e minus a alpha x1 minus I square root k squared minus alpha squared x2, and we will say about what's of generality x2 is smaller than 0. Why can we make this assumption? Because of the symmetry. So if we find it for this, if we find the perfect symptotics for x2 smaller than 0, we automatically find it everywhere because of symmetry of the spectrum. So, well, does anyone have an idea of how we could maybe find regions where this decays exponentially? It doesn't necessarily seem so easy to figure that out for this integral. No? Okay, well, I also didn't see it, but after reading a textbook, it will hopefully make sense. So what we do is, and yeah, I don't have any intuitive explanation as to why we do the substitution that we do now. It's one of these things that we do so that we define spectacles to it, and then you see that it's good and satisfactory. But so we define our coordinate system like this. Well, actually, for those of you that do know the method of series descent, the reason why we do that is because if you want to find the subline of this function, of this exponent rather, you will find that the saddle point is that alpha equals minus k times cosine of theta. So that tells you how to choose your coordinate system. So the choice of coordinate system is dictated by the saddle point. But even without knowing the method of sequence descent, it will hopefully be clear soon why you choose. But if you do know it, you look at the saddle point of this exponential. So we let alpha equal to this, and x1 as well. We just become the product. Right? But yeah, again, even if you don't know the method of descent, don't worry, to look in the next one. And yes, so theta is in wait. Oh gosh, I think I got it wrong. But so I've written that it's from 0 to let me check if I choose fine. Oh, okay, so I think what I want. I'm pretty sure I want to speed now like this. So then this would be like this. And this would be like this. Yeah. Okay. Maybe we'll change the later on. It does not matter, but one choice makes it easier than the other choice in the calculations. So again, it doesn't really matter, but I will draw a picture, and for one choice, the picture will be really ugly, and for the other, the picture will be really nice. So let's hope that this choice gives us a nice picture. Okay, but anyway, if we do this, then, and this is the reason for why we choose this coordinates, is we use polar coordinates, and here beta is complex, right? So this is why you can make this choice, because if you choose a complex beta in here, then this will be a proper Taylor coordinate system. What is beta? Beta is a complex, it's our new complex driver. Yes, so. But again, I will draw a picture in a moment. So then P is equal to D I K cosine beta minus beta. Yeah, I check this if this should be a plus. I think with this part, it could be a plus, but don't quote me on that. But I think with this part, it does be the correct sign, right? So what would this would yeah, but eventually you have to use that the square root of this if you have a cosine here gives you a sine. Then this will give you plus the sine, what is underneath the square root is positive. And then you have cosine, cosine plus sine, sine, and then use the difference theorem and get to this. So I think this is the right. Oof, but anyway, we will see. Is that the right one? I tell you what, let's make the break now, and I will figure out if I did this correctly. It's a good time for the break anyway. So maybe let's keep going in 5 to 10 minutes, and in the meantime, I will figure out if I did this change the way I want it. Okay.
Well, these minus K, minus K is yeah, that's nice.
Absolutely.
But I want to see that I do the yeah,
Cosine theta, and then I have minus. What is minus? Because I have the minus right here. So then I have minus.
No, but A is minus cosine.
Ah, you're right. Yeah. Oh, thank you. So I didn't by the way. Yeah, because because the minus plus here. Yeah, then I have a minus here because it's totally the minus like the other side.
But you have minus,
Yes. And then I have plus sign. It's fine.
No, minus.
Why?
Because you have plus now.
Yeah.
So you have the minus.
Yes.
The minus. No, wait, are you talking about the bottom or the top?
No, I got it.
No, but you have plus one.
Yeah. I have plus, but from the square root I get the minus. Because I have the square root of 1 minus wait. I have this, right? Wait, I have
This is the rule of the top.
yeah.
You come with a minus here. With a plus here.
Yes.
And you have a plus, you have plus, you have to the minus here, and then it's okay.
Yeah. Wait, yes, I think you're right. Yeah, so if I want, yeah, so if I have this, right, yeah.
Like this cosine of theta is cosine.
Yeah, plus minus plus. Yeah, that's no way.
The minus here, the minus eight. So you think about it. Yeah, so alpha is minus.
Yeah,
that's all the case. Yeah. So we have both sides. Right? Both sides. And then we have C plus. Square root of 1 minus cosine squared, which is sine squared. Square root, we get the sine. Betas. And then next we have this is what you get.
Oh, wait, I want my real power. I was worried about the sign up with square root, but because I want alpha, I want alpha to go from minus k to k, so I want cosine to range from minus 1 to plus 1, so the other way around. But then the sign, the real part of the sign will always be positive. So the square root is plus sign. So then by means it will always be plus sign. By means of the integration of the square root. So plus here, so it's please never have one of my lectures without okay, but people established that I did it in field. Right, of course. Yeah. Okay, so now we can. Oh, I will quickly quantify this. So we don't officially continue yet, but the reason why I want to read from 0 to pi is because I'm particular as to how the real axis is that, like where the real axis is mapped now in each coordinate system. So yeah, this is why I like this. And I'm sure that the picture time will be fast, right? I need to make sure that it actually follows.
So you want the minus beginning of theta and the
Yeah. I'm reasonably sure that this is in fact what I want. Yes, this is. Absolutely. So no, you are right. Like this was not correct, but the part that I was probably was correct. Yeah, it's absolutely. And so then it's also correct for this description of angle, because otherwise I would have the other side for the square root. Okay, anyway.
Sorry, can you repeat about the center and about the investigation of the.
Oh, yes. But don't worry. Let me use the rest of the yeah. Basically, remaining time. I want to go for the solution. I have to say, on first, okay, so it would be like that, because conference, so it would be after that, or on, let's say, I wish to know again. So, I suppose, in fact, I can also have it depends. When Sonia so maybe half an hour, it's a good idea. Otherwise, it's like on the but I must have gotcha. Must have definitely coming out of the exit without the file. So it's not like we love it at the bench of so then I think we're going on. And I have like one of the two will be appended. So now I can put a lot of meat on. Oh, okay.
That means you must do a PhD course of and it is mandatory for you.
After you finish,
Yeah.
you do the.
I can teach from six.
Well, yes.
Du wirst du das
Yeah.
So, yes. Anyway, yes. Okay, so let's keep doing this. So now that we discovered, okay, guys, this formula is completely correct. Essentially, it's because of how we chose this variable and because of how we read access is mapped into our new coordinate system, which I will go on a bit now. And also one of the reasons why we can't just blindly, so to say, use the method of least descent is, so what I mean by that is we can't just say, oh, nice, this thing has a saddle point, so I apply the method of 6 descent and I'm done. Because this would miss something very important, and I will explain to you what we would do this. It's not to say that we can't apply the method of 6 descent, we will apply it, but we can't apply it yet. Okay, so what you actually want to come is the case exponentially whenever the imaginary part of cosine of beta minus beta is greater than 0. Okay, well, I should have done the picture first, but I will finish writing this now. That is, whenever sine of real part of beta minus beta times hyperbolic sine of imaginary part of beta is smaller than 0, where I have written beta is real part of beta of imaginary. Right, so if I put beta in its real and imaginary part, you see addition theorem, I will find that the imaginary part of this cosine is given by this term over here. So this is in R and this is I. So I'm interested in finding the range of beta where this goes. So now I draw the picture that I promised you. So here, this is our alpha coordinates. This is our alpha over here. And there is my middle. So this is gamma. Here I have minus k, here I have n, here I have plus k. Okay. And now what do we have in our beta coordinate system? This is big enough probably. So here is beta. So this corresponds to, right? If beta is equal to 0, here we have k over there. If beta is equal to sorry, so if the real part is equal to 0, if the real part is equal to pi, that corresponds to plus k. And then this polar singularity A corresponds to let's make it here, theta. Right? In this coordinate system, the polar singularity is just theta. So these are our singularities. Maybe let me circle them in red. That's actually better. I will encircle my singularities in green. These are my singularities. And then gamma looks something like this. It comes from over here. So this is gamma in our new coordinate system. So let's call it gamma hat, just to make sure that we are. So everything in detail we can maybe denote. So I do it like this. It goes like this. Then like this. And like this. Okay, does this picture make sense to you? I will not derive that, like I will not prove that this is indeed the contour, but it's relatively straightforward to check that this is mapped onto the real axis and the other way around. But do you understand this picture? Okay, good. So now we want to find the region. In this, we want to just find, okay, where in here does this inequality hold, right? So this will be like, we can take these regions because, so let's call this inequality star. So from star, what will we get? What will we get from star? We get from star that we have one of the two scenarios. We have either real part of theta is in theta and pi plus theta, and pi is smaller than 0, right? This, if theta imaginary is smaller than 0, the hyperbolic sign is smaller than 0 as well. But then this guarantees that this is greater than 0. So overall, this inequality will hold. And equivalently, not equivalently, sorry, like similarly, we find that we could also have theta going from minus pi to theta. And this symmetry is why I was worried about choosing my instant angle. Otherwise, we shifted more to one side. So I wanted it to be as close to 0 as possible to have it nicely. And yes, and imaginary part greater than 0. Okay, so these are my conditions. All happy? Good. So this I can draw now, right? So here I have minus pi plus theta. So can we see that? Yeah, the red doesn't really show on Zoom, but I will use it anyway. Hopefully the page is working. So this is then theta plus pi. Yeah. So minus theta plus pi will always be smaller than 0, right? Because theta is between 0 and pi. So it will always be a little bit behind that. Because theta is very far on the right, it's only a little bit behind. But anyway, this will be over here. And this will be over here. So it will be ending behind 0 and behind, sorry, before 0 and behind pi. And then I look sort of at this region. And this will be the one region where everything became exponentially. By everything, I mean this function. And similarly, I have this one over here. Yeah. Oh, sorry. Also, this is not the polar singularity. This was completely wrong. This is really important. So, how do I say this? Okay, so this will keep being theta. This will keep being theta. But my polar singularity will be over here, right? Because my polar singularity is my incident angle, not my observation angle. Right, the polar singularity is that A hat equal to K cosine theta. Okay, so it's so it's yeah, it should be theta in love. Yeah, that's like that. Theta minus pi then, right? Because I need to get the minus in front of here, so I need to change it by pi. So now I have to make either minus or plus pi, such that the incident angle lies in between here. And I can, without loss of generality, say that my incident angle comes like between 0 and pi. Again, because of symmetry, right? If I have a half plane, so that's why the sum. If I have a half plane like this is my getter. Whether an incident where it comes from here or from here will be the same as if I look at it from down here. As in, it will not be the same, but the field, the resulting field will just be flipped, because the scatter is symmetric. So really, without loss of generality, we can assume this. And why do we assume this? Just to make sure that we can draw this picture nicely. Otherwise, you can still draw it like here, but it really doesn't matter. The important thing is you can make a choice because of the symmetry of your problem, such that you get a picture like this.
So, okay.
Was that your question? Yeah, okay, yeah. And the important part is that the line goes through theta. This is really important because this is our starting point. So we wanted to go through there. And also we have a really big problem if the polar singularity coincides with the starting point. So we will pretend that this will not happen. Okay, is this picture correct now? Yes, that's good. Do you all understand this picture? And do you understand why this was wrong? Okay, good. So we found the regions where all of this behaves coming. So now what can we do? Well, look, what we wanted to do is we wanted to change our integration contour such that the integrand decays exponentially. And we want to do that in like as much as possible. Because we want to have only very few things on the integral remaining that we need to worry about, right? So if you look at this picture, well, most of it already lies in the exponentially decaying region. So what would you do if you wanted to find, if you wanted to change gamma to a contour that decays exponentially almost everywhere? Like if you want to maximize the exponential decay along gamma, like along the new contour, how would you change that? Sorry?
You want to explain?
I said, okay.
No, you said, can you repeat the question if you?
How would you change gamma to ensure that you have the most exponential decay? Not necessarily the strongest, but right here, like along here, it doesn't decay exponentially, right? Because the inequalities are strict.
So the problem is the part that is over the axis.
Exactly, but what can you do using Cauchy's theorem? All we want to do is to make sure that we integrate over something that almost everywhere decays exponentially. Exactly, we just push it up a little bit. It's amazing, right? And this is what Cauchy's theorem allows us. So what we do, I will draw you a picture, but you don't have to choose it like this. You could do whatever. Let's I don't have enough colors. I will just use blue again. I can change gamma to a contour, sort of like this, right? So this I will call equity. So this is our speed of descent contour. It doesn't really matter what exactly it is. If you want to do it, and this is what I meant at the beginning for numerically. So the idea is that you change your path of integration such that over here, everywhere, you don't have any more oscillations. Because you have exponential decay, whereas here the E function would do some oscillation like this. And numerically, if you have exponential decay, that's super nice for your computer. So if you would want to numerically compute your field, this is the contour that you would use. But let me draw another picture. We cannot always do this. Why can we not always do this? We have the same picture, I guess. Where am I? We have the same but not quite. So like, we still have our one region here. We have, let's say we have theta over here. But you could also have a scenario where you have your polar singularity by here, right? But now, what will our situation be? Our situation will be something like this. It's a bit more otherwise, yeah. But you get the idea. We could have a situation like this. Either our incident angle is different or our observation, right? If we choose theta is what I mean by observation, right? This is where you look and measure the effective field. So you could either change the incident angle of that, or you could, in this picture, just think of moving around and measuring the field at different angles, and then theta would move all the way around here, which would shift the regions of exponential decay. But the important point is that you can have a picture that looks something like this. And now, well, now we can't really change it anymore as we did, can we?
Can we choose gamma depending on which side the similarity is?
But the problem is it always must go through this one. Exactly. So I mean, of course, what I could do is I could do something like this, which is perfectly valid. But now the problem is really we have this whole contour where we don't have exponential decay. So if we want to maximize exponential decay, this is not really the optimal choice that we want to make, right? So what do we do? Well, head first through the wall, we just do exactly what we did over there. Change our contour like this. But what we will get, so maybe make it also in green to make sure. But what we would also have to do is we would have to take into account a loop like this, right?
Interesting degree around
Exactly. So I can change this contour, but I will have to take into account this polar singularity, which, like intuitively speaking, you push your contour over it and it just, you know. The idea is that you have a hole, and if you want to move your contour over it, you will pick up a contribution of this. But again, you can look at these two contours, use Cauchy's theorem, show that if you integrate over this plus this, it will indeed be the same as this. If you don't like Cauchy's theorem so much, just think of Stokes' theorem maybe. This is the boundary of a perfectly smooth region, so you can integrate over it, and you can use Stokes, which is absolutely no problem because holomorphic functions, which is holomorphic everywhere in here, are closed in C. You can't have any other way. Which is, but if we wouldn't encircle the pole, we would have a problem, right? Because then neither Cauchy's theorem nor Stokes' theorem apply. Equivalently, we can just take the pole and use that theorem, which will be absolutely what we're doing here. So it's really a matter of case. But the idea is that as we want to get this contour, because this contour will maximize our decay. And to get this contour, we need to take into account this pole. Only sometimes. We only need to take into account the pole if it lies over here. Because if it lies over here, sort of our real axis is like moves around the pole in the correct way. So here we can just change it up without any problem. Does it make sense to you? This is super duper important for everything that we will do in the remainder of this course. So if you have any questions about this, now's a good time to ask. Okay. So, yeah, let's maybe write down everything that I've just said. So we can change gamma to a contour as the field. So that the decays exponentially and everywhere except at gamma. And also, so now that's right. So change control to contact STC. STC is this over here. So STC is our deepest descent control, which is the control that goes from here over here. But we are not actually doing numerical computation. So how exactly will parameterize your line? But doesn't really matter. All that matters is that we can change it into something where they have exponentially. That's all. I have made the star. So my star is where do I write this? So that was what, so we can change gamma to a control STC after taking eventually, I will write down the formula in a moment, after taking eventually into account a contribution of the point A. So that indicates currently everywhere except at theta, where we can never decay, right? This is simply because of the region of where our functions decays exponentially are dictated by theta. And they go up to the one side and down on the other side. But theta itself will have no open neighborhood whereon everything decays exponentially. You will always have some parts, but never other parts. So theta itself must always remain such that the integral decays non-exponentially. Does not decay exponentially there, sorry. But we can never achieve exponential decay, and of course this is because theta is the power. But like this picture is what is sort of the reason why all of the method of sequence descent and subatomic method works, right? You can also do it in higher dimensions, but really the idea is that there's some point, no matter how hard we try, we can never get exponential decay in this point, in the limits of subatomic. And so this is only if you want to look it up on the internet.
So sorry.
Yeah.
You go after taking you go
After taking eventually, because we don't need it we don't need it all the time. So long story short, this explanation was my quote proof. It wasn't like really as rigorous as a proof, but I hope all of this makes sense. So what do we get? What do we get eventually? Overall, we get that, and I will write everything for the coordinates now, is equal to 1 pi SPC of phi, let's say theta, right, how do I do this? Okay, let's maybe call it, I will write down what phi hat is in a moment. So we have phi hat of theta And then we have and then we have E I A R cosine beta minus beta b beta plus 1 2 pi and then product small gamma line so gamma. So this is A hat and gamma moves around at once in the clockwise direction. Cosine beta minus beta p beta and all of that times minus pi where this is for once not our beloved angle function, it is the heavy side step. So this is because sometimes we do get this integral, sometimes we don't get it, and whether we get it depends on the relative position of theta and theta n, which we write by this. Sometimes it's 1, sometimes it's 0. And what is by head of theta is k minus k cosine theta n k plus k cosine of theta, and then we have minus k cosine beta plus k cosine. Okay. This is yeah, this is essentially just this and this instead of alpha I've written k cosine beta minus cosine beta, sorry. Okay. Well, if I did everything correctly, but please check it for yourself. So also, this formula is valid everywhere. This does not, this is no asymptotics yet, right? We tried to get to asymptotics, but this is perfectly valid without any asymptotic, without doing any approximation. And so this is completely rigorous, as in non-rigorous. So if I did everything correctly, we will get something like this. So using the residue theorem, we then find that the theta field is equal to 1 2 pi SDC blah blah blah. Yeah, it's 10. Minus E minus I K cosine beta plus beta n times our difference. Okay. Why have I written it like this? Because this is exactly the reflected wave that you would get from the beginning using ray optics, right? It is just a plane wave that is present in some region, and the region where it is present is, if I find it like this, it's exactly over here, or if it comes from down here, it's over here, right? So this is the reflected wave that you would get using doing what Newton did at 304 years ago. Which specifically means that this over here is our diffractive value. So this integral over the steepest descent contour is everything that we get from the corner. It's everything that is not taken into account by classical ray optics. So really, when we want to do our Hartley asymptotics, it just means finding a Hartley approximation for the diffractive. So this we can call, or people call, the reflected field because it's reflected back.
No, it doesn't depend on that.
Sorry?
It doesn't depend on
No, it does depend on R.
maybe.
No, it does depend on R. Sorry, yeah. Absolutely, sorry. If I ever forget an R in the exponential, we will always have R in the exponential. So, yeah, but very good. Okay, so the important part is that the scattered field splits always as a refracted plus reflected field. So, yeah. And again, this doesn't need any approximation. But what can we do now? Now we approximate it. So it's cool, right? Just by doing some appropriate concept information, we will cover exactly what we expect from the classical theory, plus some correction term that our new theory, that hopefully is a correct theory, gives us. So I kept this over here because you will need it. So now let's take infinity. And now definitely like well. So the method of steepest descent tells us that I can approximate this integral by the value of beta hat at the saddle point. So using the method of beta, and we find that the scattered field is as R goes to infinity, up to terms decaying exponentially, it's approximately phi hat of theta times the SPC contour, T minus phi a, is it? Well, it should be plus. Okay. And yeah, right. So essentially, as I said in the beginning, the idea is if you have this significant contour here, and if this is the only point where your integrand does not decay exponentially, you can just look at these lines where your field decays exponentially, neglect them. But because this is the only point, you can really make this as precise, not as precise, but you can make this as close to this point as you would. So approximately, as you take this limit, you will only this will remain. And then the integral like so. But this is a direct application of the method of steepest descent. So if you don't believe me, this is, if you have an integral like this approximation is exactly what the method of steepest descent tells you what happens. And again, the idea is that we neglect this and this. But we can still write this. So we will approximate this as well, but we don't necessarily have to approximate at this point, right? This is just like more, without approximating this will just be more accurate in some sense. Does this make sense for you? Okay. And again, if you want to have the mathematical proof, it's a one-man application of this one. Good. Oh, sorry, I forgot something very important. I should have here. k times. Fine, but I strategically left enough space on here. Fine, right. Because it's if I write the eta in our integral, I did not account for the factor that we get from the change of coordinates system. After we change our coordinate system, you know, the change of coordinates is perfectly valid, but I just forgot to take this bit into account. So please write it in the definition of eta hat. So now this is a fact. Pi times. So this integral is exactly our Hubble function of the first kind. So it really appears over and over again. Yeah, just like it. So this is how much time do I have? Well, I don't have so much time left, but yeah, I think if you are interested in the proof of this, I can send you something. Okay. It's not straightforward to prove this relation, so it's not obvious, I think, by any means. What you can do is, or the way that I proved it, is you can look at this, you can check that it satisfies the Bessel equation, and you can check that it satisfies the radiation condition. But then you know that there is exactly up to maybe a scalar. That there is exactly one function that solves the Bessel equation and satisfies the radiation condition. So we know that this up to some scalar must be equal to the Hankel function. And the scalar we get because sort of by the constant that we get from plugging it into Helmholtz equation, right? So we would want something like that. We would want to satisfy something like this, where we have the data distribution on the right hand side. So this equation will determine the factor that we get. But if you want to make it rigorously, you have to work with it in the distributional sense. So it's not straightforward, but I can send you something where it's true. So just take it as a tangent for now. Okay, but now that we have accepted that it's a Hankel function, we can either leave it like this, which is perfectly valid, but what people usually do now use the asymptotic extension of H10 KR as infinity, and find that the effective here as R goes to infinity. It is 3/4 I pi divided by 2 times. And so the asymptotic extension, look it up in Wikipedia. It's don't bother about proving asymptotic extension of our functions. You know, we are just betting that some people figured out also in the last century. So how you get to this expression from this expression is just using a bunch of geometric identities and work from alpha on C. And here we have C I K R divided by square root of K R. Okay, so this is the approximation of our diffracted plate. And this was the goal to find this expression. And as you see, we really do have a problem when theta is equal to our incident angle, because then this expression doesn't make sense anymore. Which is essentially because the total time and the polar singularity are the same. So then what we would have done in the method of theta is we would have approximated the integral by its value near the polar singularity. So naturally that should be infinite. So the important thing is that this approximation is not valid everywhere, but we will not worry about trying to find an approximation that is valid everywhere. If you want to do it exactly, compute the integral. Well, compute this integral over here. And numerically, this will be reasonably fast. And in fact, this is how the pictures that I sent you 2 weeks ago are computed. Okay, this. You can also use, there's a lot of stuff you can do. This is not explained in my thesis, but it's explained in Nobel's book on like methods versus the dynamic method. You can also rewrite this in terms of Fresnel integrals. And Fresnel integrals, they are almost as fast as Bessel functions, meaning that computers will very well comprehend them. And as a this mentioned all our available as well. I didn't use Fresnel integrals because we already had sort of the Ankel functions, Bessel functions, so I think let's go that route. But usually what we do is that we run it in terms of Fresnel integrals, and that's super happy that this is something very well studied. But yeah, anyway, if you want an approximation, do it like this. Keep in mind it's not valid everywhere, and if you want something that's valid everywhere, take this. Good. So that's the mathematics for this week. I have 4 more minutes. I think I will try to show you some pictures that we get from this, because now that we have computed the different components of the far field, we can plug it in. And this is, even if you know no numerics, I'm confident that every one of you will, knows how to plot this function. Because you just need to Mathematica on MATLAB, or just ask ChatGPT, write me a code for plotting this function, and we'll be able to do that. So really, it was not about the picture, right? And today, and using codes, but we will do all of this in 2 complex variables starting next week. So maybe we won't do exactly that in higher dimensions next week, but next week we will. Well, I will try my very best to give you 1.5 hour crash course on several complex variables to not prove anything, but to introduce the concepts that we will need. And then what we will do after that is we will introduce some mathematical machinery for approximating 2-dimensional Fourier integrals. So that will be maybe the second half of the course. How can we deal with such types of integrals in higher dimensions? And I will only give you physical examples for where such integrals occur, but I will not talk so much about physics anymore. So it will mostly be approximating integrals in higher dimensions from this point onwards. Anyway, what I wanted to, so yeah, it's in my PhD field, so you can look it up. But these are the pictures that we get from just plotting what we do, right? So down here we see the diffracted wave, which is only this. So while this picture doesn't really show it very well, but you can see it bends around over here, it bends around over here and over here. These lines is where it blows up. So if you are plotting this, you have to tell MATLAB or whatever program you use that it should please cut the value at 2, I think I used here. Otherwise, this will just be super red and you will not see anything. But you can tell MATLAB to cut it off. You can specify the range for which it should plot. So that's what I did here. So yeah, here it's not valid. Away from these lines, it's a perfectly valid approximation. Here we see the geometrical object components, that is, we just see the incident wave And here we see the incident plus the reflected wave, which is sort of what you would expect using geometric logic. Specifically, you would not expect anything in here. And then on the top is just, if you sum it all up. And I think the right is Neumann and the left is Dirichlet. So we've only done Dirichlet, but similarly, you can analyze the Neumann case. And this I've done for my thesis. So, but it really works pretty much exactly the same for everything that we see today. Yeah, and let's maybe look at this and so this is not in my thesis, this is Matthew Nethercott's thesis, but you can look this up on the Universities of Manchester homepage. Yeah, here we go. Okay, good. So here you see the exact versions, and here you see the approximated versions, right? So, well, modulo flipping, what you see is if you, as you would expect, if you compute this directly, the lines of this continuity are smoothed out. But also away from these two lines, this really looks like approximately the thing that you would get using it exactly. So, except for two singular lines, this really is an easy way of understanding the Farfel behavior. And that was the whole point of doing it today. One other important takeaway is that here it was reasonably, well, not simple, but we could do it all explicitly because we knew exactly what our function was, right? We knew exactly the integral that we were trying to approximate. What will be really important is that we can do everything that we did today, even if we don't know our spectral function phi explicitly. All that we needed for today was we needed to know how does phi behave near the saddle point and how does it behave near our polar singularity. Even if we would not know phi everywhere, as soon as we know the behavior near those two special points, we can write down Farfel expression like this. So this will be important because in the higher dimensional setting, we have not yet found the spectral function, but we have found its behavior near those corresponding spectral points. So we can still approximate the integral, even if we have not explicitly solved the corresponding problem. So that's really important because essentially what this is our spectral function approximated near the saddle point, and this is our spectral function approximated near the polar singularity, taking into account when we need to worry about this. And yeah, I think this is a good point to stop. So yeah, I'll just stop the recording. I want to terminate. Yeah, we're done. I'm just struggling with